Hey everyone, still Mr. Thrasher, still at a distance learning. I hope you had a nice spring break. In this video, the first content video, as we pick up where we left off, we're still trying to learn about light. Okay, light is, again, the focus of this unit, but we're still just trying to work in what exactly is light. Okay, from our last week or the week before spring break, we learned a little bit about light, or we remembered a little bit about light. And from our activity, hopefully you saw evidence that light acts as a wave. And that's an important idea and a debated idea. Isaac Newton, for example, he actually did a lot of studying with light. He believed light was a particle. One reason was he did a lot of studies of reflection, light reflecting off things, think of a mirror, and particles do that kind of reflecting. It's almost like bouncing. Taking a rubber ball and you bounce it off a wall, it bounces back, it reflects. So Isaac Newton was firmly in the camp of light are particles, or light is a particle. But as we've seen, other scientists came along and they did experiments, interference experiments, and they saw that, yeah, light is interfering just like sound waves, just like waves in general. There we go. So now we know that light is a wave. To be honest, even though we're still going to use the wave properties for most of light in this unit, the story doesn't end there. The story doesn't end with, all right, light's a wave. Gets a little more complicated, and that's what this video is going to get at. Still, particle, wave, what's going on with light? That's what we're going to figure out. Okay, let's do a quick reminder about particles. And when I say particles, I mean like things with mass. Again, think of a ball, think of like a Nerf dart, matter. And it's pretty intuitive, even if you never took a physics class or a science class, we know from our own experiences how matter, how particles behave. For example, we know that particles are more or less in a given area. Now, there might be like a small particle and a large particle, but we can point, we can say, oh yeah, the ball is right there. The couch is right over there. Okay, what the term is localized. They're in a given spot in space. Okay, we also know that particles can interact with other particles. Think of playing pool, playing billiards. Okay, if I throw one thing with matter at another thing, they interact. And we actually use this interaction. We studied it last semester with momentum. We also know that particles have energies, and one energy is associated with like speed. Okay, so we know how particles, things with matter, normal stuff behaves. Okay, that's important to remember. We also spent the week prior to us going on to spring break, we learned how waves behave. We learned what waves are, and we learned that waves are different than particles. And when I say different, it's how they behave. Okay, I don't know if we have to see both of these videos because we already talked about them. One way we know waves behave is they interfere with one another. If you have one pulse here and one pulse here, when they meet up, if you have crest and crest, you get something called constructive interference. But also, waves do not bounce off like particles. Remember, I really tried to stress that, and this is the reason why. After waves interact in the middle, they continue going. That's a very wave behavior, okay? So we know that waves, they're not exactly traveling particles, they're traveling energy. We know how waves interact and how they don't interact. So these two very different camps. We have particles and we have waves. And so that's why in the beginning, when scientists and philosophers were studying light, they were trying to figure out what's the category that light fits in. Okay, if we have these two things, there's either particles or they're waves, where do we put light? Which section does it go in? Well, okay. I'm going to skip this. We already talked about the interference pattern. We watched this video for one of my activities. I want to show you a classic experiment that helps show that light, again, is firmly in that wave camp. This is something called an interferometer. It's actually a very common tool used in physics. It's used both in like astronomy, studying stars, but also studying like small scale things. It's even used to study gravitational waves. Let me talk about what happens. You have like a laser, and it shines a laser, and the laser beam gets split. And one part of the light hits a mirror and bounces back. And here's what I mean about it being split. Let me pause right here. Pause. So here I have a laser. It's shining light, and this is just a tool that kind of splits the light. Some of the light goes this way, hits a mirror, comes back. Another part of the light goes this way. They're 90 degrees from one another. okay? And then it gets recombined, and then this is almost like an X-ray screen, or it's like a detector. It's seeing how much light or what's happening when those two recombined waves come together. Let's hit play and let's keep going. Come on, technical difficulties. Aha. Well, we know that based on how crests and troughs and crests line up, we can get constructive and destructive interference. So you could actually take these mirrors and you could change their distances. And by changing the distance, it's going to affect whether you're getting crests and crests lining up or crests and troughs lining up. And remember, this is what we saw in the activity. That affects the brightness, because if you have destructive interference, it gets very dim. Constructive interference, it gets very bright. Scientists use this, and we can measure things like distances. We can, again, see that light has a very wave-like kind of property. Okay, this is a very common tool, interferometer. So, again, just more evidence. Light, oh my gosh, it's a wave. So after Isaac Newton, who thought it was a particle, we seem to now be pretty firmly entrenched. Now we know that light acts like a wave, except there was a pesky individual in the early 1900s. His name was Einstein. Oh, Einstein's coming back in this unit. Einstein wrote a paper when he was studying light. And he made an experiment. He did an experiment. He had some observations. And then later on, he did some theoretical calculations and proving. And what he saw is something known now as the photoelectric effect. And the photoelectric effect presents a problem. Einstein has an issue with the wave property of light. And I want to show you this photoelectric effect before I continue on with my slides. Here's the setup. I have a flashlight. This is just going to emit a type of light. Maybe think of it as like a laser pointer. Okay, and right here I have a metal plate. This is zinc. I could change the metal plate, but I don't need to for this experiment. Imagine I just have a metal. It's a metal zinc. And these dots represent electrons. There's a battery here because and Einstein wanted to have like a positive side of the metal and a negative side. Remember, if I just plop down an electron, electrons are attracted to positive things and they're repelled from negative things. Now, normally if I don't have this light on, okay, there's no light. I mean, I already started this simulator, so let's give this a second. Here's just the metal. The metal's just hanging out. If I attach a piece of metal to a battery, not a whole lot happens to any atoms or electrons in that metal. But what Einstein saw was that when he shined light on the metal, well, all of a sudden, that light had energy and it knocked off electrons. Okay? So this light is coming in and it's knocking off electrons. I don't mean the electrons start wiggling back and forth, back and forth. That would be a very wave-like approach. Instead, this light is coming down and almost like it has momentum. It's colliding with the atoms and the electrons that are in this metal, and almost as if this light has kinetic energy, it seems to transfer kinetic energy to the particles. This is a very particle-like quality. Waves shouldn't do this. Maybe you get electrons wiggling back and forth, kind of like how ocean waves make a boat go up and down, but these particles are getting knocked clear outside of the atom. And not only that, this is really the bigger deal. If he changed the type of light, this is a type of ultraviolet light. Okay, ultraviolet light has a lot of energy, gives you sunburns. If instead Einstein shined, let's say, red light never knocks off an electron. We could stand here all day, all year, and we'll never see a single electron bounce off or get knocked off. Not only that, it seems the intensity, kind of like the amplitude, even if I cranked up the intensity, imagine instead of one laser pointer, I had 1 billion laser pointers. With more light, that also never gets an electron to get knocked off. Einstein finds out, and then later scientists like de Broglie and others, that the energy of light, it's not coming from the intensity, it's coming from the frequency. Whether you have a lot of intensity or not, it doesn't matter. You have to have a high enough frequency to get electrons bouncing off. And that's not true with a classic understanding of waves. Even if you had a weak wave, if you sent it for days and years and millennia, it should still be able to impart some energy, and that energy should just kind of be wiggling back and forth. This is a very particle-like property. This is almost like you need enough energy in that fastball to break a glass bottle. The light needs enough energy, in this case now coming from frequency, that's new, to knock loose electrons. The intensity doesn't matter if you don't have the right type of light coming in. So let me go back to my slide. I like that animation. Here's a picture of what it's already showing. Okay, so here's that metal plate. Oops. Here's incoming light, and it's knocking loose electrons. Einstein, and again later scientists, you could calculate the energy of light. It's not based on amplitude, it's based on what you would classically call the frequency of the light. And by studying the metal, you could figure out how much energy you need to knock off an electron, kind of like how bound those electrons are. And you need the same amount of energy or more. If you have red light, which doesn't have as much energy, even if you shined red light for days, you can't impart enough momentum to get the particle or the electron to bounce off. This is very much like particle interactions. It doesn't match our understanding of waves. Oh my gosh, our story just got more complicated. Einstein comes around and says light isn't like a wave simply, it's like a particle. This is the same photoelectric effect. This is, by the way, what solar panels are. If you have solar panels on your house, of course you know what solar panels are. They're pretty big the last 10, 15 years. Solar panels use this photoelectric effect. They use a metal that has enough energy or doesn't have too much energy so that regular old sunlight can knock loose electrons. And then these moving electrons, they create a current, which creates electricity. Okay, so oh my gosh, we've talked last week that light was a wave. Einstein comes around and sees all this evidence for light being a particle. What's going on? And here is our conclusion based on all these scientists. And to be honest, Einstein and some other scientists who also studied light and quantum mechanics later on realized. And I like this analogy right here. And by the way, I stole this diagram from a video from Bozeman Science. Maybe you've heard of him. He has some great science videos. I recommend you check him out. I stole this example because I saw his video and I thought it was fantastic. But here's an example. Imagine you have an elephant and you have all these scientists, but the scientists are blindfolded. And their only way to measure, to conduct an experiment on what this big object is by feeling it. And so an elephant has so many different parts, so many different properties, that depending on where the scientist is, just by feel, just by looking at it one particular way, they're going to deduce different things. It's a wall, it's a fan, it's a rope. To be honest, before Einstein came around and gave a more complete approach to what light is, this is what scientists were doing more or less. They were approaching it from, is it either a wave or is it a particle? They had blindfolds on. There's something known as wave-particle duality. Light is both a wave and a particle. And that's tough. That's really tough for our minds to grasp because that's not intuitive. On our scale, things are either waves or particles. But that's actually not true. Light has components of both. And in fact, everything has components of both. It's actually not true that you either have waves or particles. Everything has both. Waves have particle properties. That's just tough because you need to look at really big waves in order to see that. Okay, or very small waves. And particles as well. To see the wave property of particles, you need really massive particles. On our scale, human scale, our experience right in the middle, we don't really see both. But it's true. Waves and light in particular, that's our focus, acts like both a wave and a particle. Hopefully you've read some of these bullet points. Okay, now this isn't really important. We're not going to spend a whole lot of time on this, but this is an example done known as the double slit experiment that showed that particles like electrons also behave like waves. So again, here I have now, instead of a laser pointer, I have like an electron gun. It fires off electrons. Okay, so imagine I take this gun, it's like a machine gun, and I start firing off electrons. And it's gonna hit this wall that has 2 slits in it. I mean, most people would expect this, right? Because those electrons can either go through this slit or this slit, and particles go in straight lines. You're either going to hit here and gather up. Imagine this is like a collection plate, or here and they gather up. But when scientists do this experiment, they literally do this experiment. They get a device that fires off electron after electron after electron. They have these 2 slits, and they have a detector, almost like an X-ray, think. And it detects when an electron hits. They don't see this. If they set up this experiment, they see the same interference patterns with electrons, showing that electrons, particles, have wave-like properties. You actually could do a thought experiment. I saw this online a few years ago. If you did this experiment with kittens, if you had a kitten cannon, if you fired kittens at a double slit, you would also see this interference pattern. But because kittens are pretty big, right, they're much bigger than electrons, the scale of this setup would have to be ginormous. And some mathematicians and a scientist did the calculations. If we had a kitten cannon firing cats at double slits, how far away would the screen have to be so we detect cat-kitten interference? The screen would have to be several hundred quadrillion light years away. That's in fact larger in distance than the observable universe. So again, regular matter like us, baseballs, cars, ants, they have wave-like properties. But to see those wave properties, you need to be looking at a much larger scale. And this is a big part of what the science of quantum mechanics gets into. Okay, you're studying duality a lot if you go to college and you study physics and quantum mechanics. We're not going to get that far into it. Okay, so here's where we're at. Okay, light is both a particle and a wave. And in fact, everything is a particle and a wave. It's not true to think of things as just particles or just waves. They're really a mixture of both. Okay, and that's why you might sometimes hear this light as a wave, light as a particle, because it's really both. But so are you. So is your iPhone. So is the computer, so is the microwave. Everything has wave and particle components. They have what's known as duality. They are not separate quantities. I like these 2 little memes here. You're going to do a little bit of research this week to look at how scientists and how we as a society sometimes use the wave particles of light to accomplish things, and sometimes use the particle aspect of light to accomplish things. But okay, light, is it a wave or a particle? That's not really a valid question. It's both. All right, thanks for watching this video.